In this video, we define entropy for a gas expansion. Alright, so there's a variety of concepts that we need to introduce before we can come up with an equation for the change in entropy in a gas expansion. One of them is the concept of a microstate, which can be easily discussed in the context of positional entropy. Let's take a look at the top diagram here in the whiteboard. What we have here is two bulbs that hold only 4 molecules of gases. And the question that we're asking is, well, which of the arrangements that we have put here is more likely? Is it more likely that the 4 gas molecules are on the left bulb, or perhaps 2 and 2, or maybe the 4 on the right bulb? Well, we can actually clearly see that in principle you would expect that the most probable arrangement would be one in which the 4 molecules distribute evenly in between the two bulbs, right? But there's actually a way to quantify that, and that is by using the concept of a microstate. Okay, so the question is, well, how many possibilities do we actually have for the arrangement right here? And there's only one, and that is that the 4 molecules, which we're going to call A, B, C, and D, are in that left bulb. Okay, but if we go to now this arrangement, 3 on the left and 1 on the right, you will have various possibilities, right? You will have that A, B, and C are in the left, but D is in the right, or A, B, and D are on the left and C is on the right, A, C, and D, and then B, or B, C, D, and then A. Notice that there's 4 possibilities, okay, for 3 and 1, but only 1 for 4 and none. Okay, so in principle, this is actually going to be more probable than that one by a 4-to-1 probability ratio. Okay, right, so that's what a microstate is, right? A microstate is each one of these possibilities. And notice that the larger the number of microstates, the larger probability it is. Okay, we can go to this situation and then figure out how many microstates we have. We'll have A, B, C, D, A, C, B, D, A, D, B, C, and then B, C, A, D, and then we will have B, D, A, C, and C, D, A, B. Alright, so here we have 1 microstate, here we'll have 4, here we have 6, and obviously here we're going to have 4 and 1. Okay, the important thing about this is that there is a direct relationship between the probability of an event and the number of microstates. And we're going to write that as simply the probability is equal to a constant times the number of microstates, which we call W. Okay, that is what emerges from this discussion. Now we have considered here something that is called positional entropy, in which we're looking simply at positions, but something similar will happen with energy microstates, not only positional microstates. Okay, so this definition of a microstate is going to be necessary when we introduce entropy in just a few minutes. All right, now we move on to the bottom part of this whiteboard, in which we're going to try to look at the probability of gases to be in any given part of a container. Okay, so here's the setup. We have a gas in between in this container, and we're going to be asked what is the probability that one particle is inside this volume, or maybe only the left half of that volume, or maybe the left tenth of that volume. And we're going to do that according to the number of particles of gas that we're examining. Okay, so let's think about just one particle. If we ask, well, what is the probability that the particle happens to be inside that volume? Well, the probability is 1 if the particle is inside the box. Okay? But then we can ask, well, what is the probability that the particle is now on the left-hand side of that box? Well, that actually is going to be only 0.5, right? 50% of the time it will be on the left-hand side of the box, 50% will be on the right-hand side of the box. And if we ask for the probability for that particle being in 1/10 of the overall volume, then that will be equal to 0.1. Okay, so clearly we see here that for a gas inside a volume, right, the probability of locating that gas inside some volume seems to be directly proportional to that volume. Okay, so notice how in this case we see a proportionality between volume and probability. Now let's try to do this for 2 particles. Okay, so let's now think about 2 particles. Right, so now we're going to have 2 particles, and the question is, well, what is the probability that both particles are in that volume? Well, if both particles are inside the box, then there's no restriction. That probability will be 1. They will be inside the box. Okay, now if we think about the two particles being right here on the left-hand side of the box, well, you will have that there's 50% of chance for one, 50% of chance for the other one. Probabilities are multiplicative. So what you actually have right here is that this will be 0.25, which is the same thing as 0.5 squared. Okay, and then for the two particles to be in the leftmost tenth of volume of that box, you will have 0.01, which is only 1% probability. Okay, so that will be 0.1 squared. Okay, now obviously if we do this for n particles, okay, so we have now an Avogadro number of particles. The idea here is that we will have a probability of 1 for them being inside the box. Now the probability for them of being inside this left hand of the box is going to be very small. It will actually be 0.5 to the n. And here you will have that this will be 0.1 to the n. Okay, so what we learned from this discussion of probabilities of a gas is that that probability is proportional to the volume elevated to the power of the number of particles. Okay, so notice that we have defined probability as a function of the number of microstates in the upper discussion. Now we have defined the probability of the gas being in a region of space according to the volume. So we're actually now ready to try to introduce here what the entropy is, and then try to apply it to a gas expansion. Okay, so let's see how that works. All right, so this is the work of Boltzmann, and Boltzmann recognized that the entropy is a measure for the number of microstates that you have in a given arrangement. And the equation that he recognized is that entropy is linearly proportional not to the number of microstates but to the natural log of the number of microstates. Okay, so this is going to be the operational definition of entropy deduced by Boltzmann that depends on the number of microstates. But microstates for us is very difficult to, they're very difficult to measure. We would like to actually have them as a measure of something more easily, like for example a volume. As a matter of fact, what we want to do in this video is to come up with a definition for the change in entropy experience when you have a gas expansion of a gas, say from this situation where you have all of the gas concentrated in this small volume, to a situation in which you remove this wall and now the gas tends to occupy the entirety of the volume, right? That's what we'd like to have, a measure of a change in entropy in that gas expansion from just half of the volume to the entire volume of the box. Right, so the question is, well, how do we use all of these pieces that we have in this whiteboard to come up with an operational definition for the change in entropy in this gas expansion? Right, so let's go little by little. The first thing that we're actually going to do is to try to put here entropy as a function of the volume by putting together those equations, right? So what we actually say is that this probability is going to be equal to this probability, right? And then what that means is that the number of microstates is going to be equal to the ratio of these two constants multiplied by the volume to the power of the number of molecules. This ratio of C2 over C1, these are constants, so we can simply call this a new constant C. All right, now we come to the definition of entropy, and then what we actually say is that this is going to be equal, for this particular case, is going to be equal to K sub B natural log of this constant C, V to the n. Okay? So that will be how the entropy will work for this particular case in a gas expansion. And now we're ready to calculate changes to the entropy, which is what we really are interested in the molecular sciences. All right, so then let's figure out how this works for a regular gas expansion. Okay, so this is going to be our problem. Here you have this gas, and again, initially, that gas is going to be in a volume that we're going to call the initial. Okay, and then what we're actually going to do is let the gas expand so that the gas is in a final volume VF, right? There's going to be an entropy of this gas which is going to be initial. There's going to be an entropy of this gas that is going to be final, and we're interested in calculating the change in entropy from here to here. The process would be exactly the same as saying, well, initially all of the gas is here, we're just going to remove this wall, and then what will happen is that the gas will expand to the entirety of the volume. That is truly a gas expansion. Right, so let's calculate then what the initial entropy and the final entropy would be according to this expression. All right, what you have is that the initial entropy is going to be equal to K sub B, natural log of this constant, and then the initial volume to the n. And then the final entropy is going to be equal to constant final volume to the n. We want to calculate the change in entropy. Okay, so this delta S from the start of the expansion to the end of the expansion is just going to be the difference of these two things. Right, so I can take common factor of K sub B, and then that will be the natural log of C VF to the n minus the natural log of C VI to the n. Okay? I can apply now the properties of the logarithms to find that this is going to be equal to K sub B, then the ratio of C VF to the n over C VI to the n, which is going to give me a very nice compact expression right here. Right, notice that these two coefficients cancel, and then here you have the logarithm of a power, which is exactly the same as the following: nk sub b ln bf over vi. Okay? Well, we simply have taken the power that was multiplying the final volume and the initial volume, and taking out of the logarithm as a factor. Okay, so we're making a good break right here. Obviously, we would like to put this as a function of something that is a little bit more useful than Boltzmann constant, the number of particles. And this can be easily done because we can recognize that the number of particles is going to be simply equal to the number of moles that you have multiplied by the number of particles per mole, which is Avogadro's number. Okay, so we can come here and say, well, this is the same thing as the number of moles that we have multiplied by Avogadro's number, multiplied by Boltzmann's constant, and that is just the natural log of Vf over Vi. All right, so here we can quickly recognize that the product of Avogadro's number and the Boltzmann constant is just simply the gas constant, R. Okay, so we have come up with the definition of the change in entropy in a gas expansion. Okay, delta S from I to F in a gas expansion is simply going to be equal to nR natural log of V final over V initial. Okay, that will be the definition of the change in entropy in a gas expansion. Let's see if this makes sense. Let's calculate the sign of the change in entropy for this gas expansion. Well, what you will have is that the final volume is larger than the initial volume. Okay? So what that means is that the ratio is a number larger than 1. And what that means is that the logarithm of that number, which is larger than 1, should be positive. Right? So what that tells you is that you would expect to find a positive change in entropy as you go from here to there. Right? And that is exactly what your intuition says. Right? Systems move to try to increase their entropy. And actually what we know is that if we have the gas confined in this volume, and then we remove the barrier, naturally, spontaneously, the gas tends to occupy the entirety of the volume, right? This happens spontaneously. And again, we can see that in this particular case, that is coupled to a positive change in entropy. Entropy, gain in entropy is the driver for that particular transition, gas expansion. The contrary process actually would not be spontaneous, right? The idea of having the gas dispersed in a volume and then all of a sudden expecting that the gas compresses just by itself into a reduced volume of space, that never happens. And the reason is that in this particular case, that will lead to a loss of entropy, which again is something that is not spontaneous. Okay? Right, well, very good. We're going to finish this video by recognizing that this equation for the change in entropy in a gas expansion is something that is actually more general than this, right? So the equation that we're going to derive from here is going to apply to gas expansions and chemical reactions and phase transitions and every chemical process that you can think of, right? If we make memory of our work in reversible isothermal gas expansions, okay, we can remember that in a reversible isothermal gas expansion, we calculate the work as minus nRT, natural log of V2 over V1. Okay, and the heat in that reversible gas expansion was equal to the minus work, so nRT, natural log of V2 over V1. Okay, so notice how similar the reversible heat is to the change in entropy in this gas expansion that we have just calculated. As a matter of fact, the only difference seems to be this temperature. Okay, as a matter of fact, what happens is that we can then redefine this change in entropy as simply this Q rev over T. Okay, and notice that again, when you think about these two things, that actually is what you expect. Well, it turns out that this definition is entirely general. Whenever you want to calculate the change in entropy for a system, the only thing that you have to do is to compute what would be the heat transferred to that to the system or out of the system if the process were reversible divided by the temperature. Okay, so that is going to be entirely general, and we're going to be utilizing this expression to calculate changes in entropy not only in gas expansions but also in phase transitions, chemical reactions, and many other chemical processes. Right, so in this video we have discussed how to come up with an equation for the change in entropy in a chemical process. We have utilized the case of gas expansion because that is a fairly simple process, and we've seen how from Boltzmann definition of the relationship between entropy and the microstates, we can come up with an equation that tells you how the entropy changes during a gas expansion. In the end, we have seen that this equation that we have derived for a gas expansion is actually something more general, which is that expression, and we will find applicability of this expression to a variety of systems in future videos.